All right, there we go. We're back. Okay, now, nope, don't want that. Want this. Let's make it a little bigger. There we go. Okay, so now what do we do with that? We know how to find the angle now. That's not that hard. Um, in radians and stuff, and we know now that theta. Again, let's draw the circle. I'm gonna keep drawing this circle. I used to be pretty good at freehanding circles, but I thought, why not? I got this compass. I got weapons of math construction. Here's my radius R. Okay, so let's say we take off and we're going around this circle. All right, we're taking, or this circle is spinning. It's spinning. It's spinning. It's spinning. It's spinning. It's spinning in a uniform. And let's say it's a little 45 record from way back in the day. So it's a 45 RPM record. What is its angular velocity? How many turns is it doing radians per second? How many radians per second is it doing? If that's my criterion here. I mean, if that's what I want to find. So it's going 45 RPMs. This is actually a speed too. Okay, what's its angular speed? This is little omega. Sounds like I've always kind of joked that little omega is sounds like the love child between 50 Cent and Little Kim or something. But anyway, that's my little omega. All right, and it's in radians per second, and this is known as the angular speed. Angular speed. So if this thing is spinning around up here, spinning around, okay, that's what is known as the angular speed. And it's 45 RPM. So let's figure out what that is. So we know it's doing 45 revolutions per minute. Okay, to get rid of minutes, we go, well, let's take 1 minute. How many seconds are in it? Because I need to get this in radians per second. Well, we got 60 seconds times. I've got revolutions down below. How many degrees in radians is one revolution? That's right. It's 2 pi. There you go. Multiply this out. I wind up with 90 pi over 60 seconds, which is equal to 1.5 pi radians, because this is in radians, per second. Now, since I got my calculator here, I'll go ahead and do it. 1.5 times pi. So it's 4.7. 4.7 radians per second. Okay? There it is. Oops, there it is. Okay? Now, here's an interesting thing. What happens, how fast, I wonder what the speed in meters per second is. Let's say this thing, again, is 5.5 centimeters. And let's say R then is equal to 0.055 meters. Okay. Let's say we've got a ladybug at this juncture, which is at her center of mass, let's say, is at 0.0275 meters, and then this bug is at 0.055 meters. Okay, so I got that bug at 0.055 meters. So I got another bug up here What's the velocity of bug 1? What's the velocity of bug 2? First of all, bug 1 has to travel. They're going to stay on that same line as they're going around. But what happens is bug 1 has to go a lot faster. The one at the end of the line, the rocket at the end of the line, she's got to move it when they start doing their little circle thing, okay? Because she's got to cover a lot more ground in the same amount of time than this one. So V1, and so it depends on the radius because the angular speed is the same. V1 is equal to R times omega, which would be R1 in this case, which would be 0.055 times the 4.7 radians per second. Now here's another thing I need to tell you. These meters, they fill in for that radians. Radians are dimensionless. And so now you've got your, when you do that multiplication, .585. So go 2.59 meters per second. Now let's take a look at V2, which would be R2 times omega because the omega stays the same. It's still rotating at 4.7 radians per second. But now this one is 0.0275 meters. It's half times 4.5. And so this one would be rotating at 1.295 meters per second. Okay? That's huge. If you understand